Hello and welcome again. I hope you are having a great day. In this video, we are going to discuss about independent and identically distributed, that is I.I.D, very common. And then we'll discuss about law of large numbers. So in discussing that, let me set up the agenda first. So we'll discuss independence of random variables first. Then we'll discuss about I.I.D, independent and identically distributed. Then we'll discuss about the theory for law of large numbers, that is convergence in probability and almost sure convergence. Okay, and then law of large numbers, weak and strong. So let's start. The first thing is independence of random variables. Independence of random variables, RB I use for random variables. So what is independence of random variables? So you have discussed in the last class also, when there are two or more than two random variables, we may not always have only one random variable. So we discussed the joint, marginal and conditional probabilities for two or more than two random variables, and continuing that we'll discuss the independence of two or more than two random variables. So what does that mean? This means that the outcome of one random variable does not impact the outcome of other random variable. For example, so this is, I'll write it down, means that outcome of one random variable does not impact the outcome of another random variable. And let's write all the formulae. We know this. Okay, let's write all the formulae for each of the cases. For the CDF, that is cumulative distribution function, PMF, PDF, expectation, variance. So all these things, I'll just write the formulas so that you know formally that in case of two random variables, what should be the, how do we identify whether two random variables are independent or not. So first of all, let me write for the CDF case. So for CDF, we will have, so it's simple. So we know from the past that in the case of events, right? So the formula will be in the similar lines. So let me write it down in case of this. So for, if we write fxy, x comma y, this capital F is for the CDF. This is the symbol. This is equal to f of x into f of y, y of y. So the combined, okay, joint probability is the product of the probabilities. Then this is these two variables x and y are independent. So this is in context of x and y. Okay, so if now CDF is there, so next is, like, for example, PDF. Let's see the PMF, the discrete case. So this is for discrete. So these are simple formula, you will know this. So this will be probability of x comma y given xy is equal to probability of x into probability of y. This is at that particular point, what is the probability? If these two are, that is the product, then these two variables x and y are independent. Okay, so let me write one more generic form of this also. So it can be, as I said, it can be more than two random variables also. So this can be, you can generalize this and write that f of x1, x2, so on till xn, and this will be x1, x2, so on till xn. This is equal to product of I equal to 1 to n fxi of xi. So this symbol pi, earlier we saw sigma, this was summation. Okay, this is for product. This is equal to, like, this means that this is equal to fx1 of x1 into fx2 of x2 and so on till fxn of xn, like that. Okay, this is what this means. This is product, this pi symbol. Okay, discrete case, this will be product of x and y is individual products, because there is nothing common. The outcome of one doesn't impact the other. Let me write for the PDF also. The PDF would be, what will be the PDF? I'm just writing it in the symbolic format. So this will be, this is small f, right? F of x comma y is x comma y. This is fx of x into fy of y. Okay, so this is a continuous case. These are written discrete. And now expectation. So in terms of expectation, let me move to the next page itself. So if we have expectation, similarly expectation will be expectation of x comma y, or it's written xy, not like that. Xy is equal to expectation of x into expectation of y. Okay, then we'll use this to generalize. So generally, so we'll discuss variance also. For in general, so a general formula for variance of two variables is, what is it? So generally we say variance of x plus y, if that summation is there, right? So that is variance of x plus variance of y plus 2 into covariance of, we have seen covariance of x comma y. We have seen covariance in the past, in the last classes. I'll put the link if you don't remember. So what we know about the covariance? Covariance we know already. Covariance of x comma y is equal to expectation of xy minus expectation of x into expectation of y. Okay, but for independence, we know if this is independent, these two terms are equal. So what does this mean? This implies covariance of x comma y will be 0 for independent RVs x comma y, because expectation of xy and expectation of x into xy, this is both are equal, so this will become 0. That's what I'm saying here. And if this becomes 0, what will be this formula? This term will become 0. So what will be the variance formula for independent case? So for independent, RVs, random variables x comma y, variance of x plus y is equal to variance of x plus variance of y. Okay, here the formula is there, this is there, this is there, and then these two. Okay, simple products. And there's one small twist in the this, because this has become covariance is 0. We know that from the past also, we have discussed this. Okay, so these are the formulas. So let's understand this with a simple example also quickly. Say for example, if the setup is, I toss a coin and I roll a die. Okay, this we have seen this example 1. Toss a coin and roll a die. So will these two random variables be independent? So what will be the for x is equal to, let me formulate, 1 if head and 0 if tail. So this is for the toss, and y will be all the outcomes, right? Y will belong to all the outcomes. This is how we write it. Y will belong to all the outcomes of the die when we roll a die. Okay, so what's next? So what will be the all possible outcomes? So here you can clearly see that both the random variables are independent. If I get a heads, it doesn't impact whether I get a 2 or a 3 or a 5 if I roll a die. So these two are independent. What will be the outcomes? So generally all the possible outcomes will be, we'll get a head and 1, head and 2, like this till head and 6. This is 1, and then either we'll get tail and 1, tail and 2, and till tail and 6. So these are the possible 12 outcomes. 2 into 6, 2 from here, 6 from here. This will be 12. So these are possible outcomes. And here obviously x and y are independent. So this is a case of independent, because we can write x into y. Expectation of x is expectation of x into expectation of y. Let me give you one more concrete example. I'll give you many examples so that it's very, very clear. Okay. So I'll give the second example. So with this you will understand a bit better. So this time the setup is toss a coin twice. Toss a coin twice. So what will be the possible outcomes here? Head head, head tail, tail head, and tail tail. And now we count the, so now how am I defining my random variables? So let's define x is equal to number of heads and y is equal to number of tails. So what will be this? This will be either 0 or 1 or 2, and similarly this will be 0, 1, 2. Okay. So now if you see, are x and y independent here? If I know that I have got 0 heads, then can I tell that I have got 2 heads? So these two events are, or these two random variables are mutually exclusive. They are not independent. So x and y are not independent. So this is some intuitive example. Then we'll apply the formula also. Simple examples, right? So let's do a problem where we will apply a formula. So for example, say for example 3. So let's consider a uniform random variable. So let's see, we have a uniform random variable. Okay, this is 0. And say it is coming from -1 to 1. So my range here is so -1 to 1. This is my b equal to 1 and a is equal to -1. This is my range. So if this is -1, this is 1, what will be this value? We know that from the PDF formula this area should be 1 complete. So this is your PDF, right? So this area should be 1. This complete length is -0 to -1. This is 1 unit. This is 1 unit. So 1 plus 1. This is total is 2 units. I'll use a different color. So this total length from here to here is 2 units. So if this is 2, area is equal to 1. So what should be this value? So this will become half. 2 into half is equal to 1. The complete area of this rectangle. The length is 2, so the breadth should be height. And this is my uniform PDF, that x is equal to half. So you remember, so what will be the expected value here? Expected value will be 0. So let's write it down. So this is a uniform distribution. Uniform distribution. B is equal to 1, A is equal to -1 from B to A. So expected value of x is equal to mean is equal to B plus A by 2, that is equal to 1 minus 1 plus -1. 1 plus -1 by 2, that will be 0. Okay, so how will we write fx of x is equal to 1 by B minus A, that is equal to half for -1 less than equal to x less than equal to 1, 0 otherwise. So this is my uniform distribution. Okay, so this is my x. So this is about x, and let's define another random variable. So there is another random variable y is equal to 2x. This is my x and this is my y is equal to 2x. So let's compute what will be the this value, the expected value of xy, whether it's equal to expected value of x into expected value of y or not. So what will be the expected value of xy? Let's compute the LHS first. Xy is equal to 2 times expected value of x into y is 2x. I have defined it this way. Is equal to expected value of 2x square. How do we define? How is expectation defined? Let me just check. So expectation of x is defined as, this 2 is constant, so this will come out. So this can be written as 2 into expectation of x square. This is expectation of 2 or a constant value is the number itself. So that's why I have brought it outside. It will be 2 times expectation of x is minus 1 to 1. So I'll put it into fx, that is x into fx. That is x into fx of x for PDFs. This is the PDF of fx of x. So what is the PDF? We have seen this. This is e minus a, that is half. So this is equal to 2 times minus 1 to 1, that's the range. X into half dx. Fx of x is defined as minus 1 to 1. In this range, minus 1 to 1, this is defined as half. It's 0 otherwise, so remaining things become 0 anyways. So this will become 2 into half, and this will become, sorry, this is x square, right? So this will become x square. This is x square dx. So expectation of x is x into, expectation of x is x into fx. Expectation of x square, here we have x square, right? So x square would be x square into fx of x dx. This is my PDF. If not, revise the expectation clause. Okay, I'll put the link in the description. So let's carry it forward. What will be the value? This will be 2 into half. This is 1, so this goes off anyways. And the remaining thing is integral of x square dx. Integral of x square dx is x cubed by 3. And what is the range? Minus 1 to 1. This will be 1 by 3. I bring it out. X cube, that now I'll put upper limit. 1 cube minus of minus 1 cube. This is equal to 1 by 3 into 1 cube is 1, and this is minus of minus 1. That is equal to 2 by 3. So expected value of xy is equal to 2 by 3. Okay. And what will be the expected value of x? This is 0. What will be the expected value of y? This is equal to expected value of 2x, because y is equal to 2x. So this will be 2 times expected value of x, that is equal to 0. So this implies expected value of x into expected value of y is equal to 0 into 0, that is equal to 0. This is 0. This is 2 by 3. This implies that expected value of xy is not equal to expected value of x into expected value of y. This is not equal to, this is 2 by 3, because 2 by 3 is not equal to 0. Hence, x and y are not independent. We can see it clearly from here. Y is equal to 2x. There is a clear relation. Y is 2 times of x. So this is related. These are not independent. If x changes, y will change. So there is a clear relation here. But we have proved this mathematically also, that x and y, if they are using their expected value, that if they are not equal, this means that they are not independent. But there's one more thing, that, so there's a note. Okay, if expected value of xy is equal to expected value of x into expected value of y, then we cannot say for sure that x and y are independent. The inverse is not true. We cannot say that x and y are independent. I'll give you an example to show this. So for independence case, we told that expectation of x, y together, the joint probability, if it is equal to expected value of x into expected value of y, then they are independent. Okay, but if this holds, the reverse, if this holds, then we cannot say that the inverse is true. If this is true, we cannot say that x and y are independent. Let me give you an example so that it becomes clear what am I saying. For example, let's continue with the same example. Okay, so we have a uniform distribution. Okay, let me make it smaller. Okay, so this is how for example 4. So this is how my x is defined. This is x, this is equal to x. So my x is a uniform random variable that is defined from -1 to 1 and whose expected value is 0. And now I define another variable z that is equal to say x square. Okay, so what will be the expected value of z, or sorry, this will be, now for example, so what will be the expected value of xz? Now we have to prove that expected value of xz, if this is equal to expected value of x into expected value of z or not. We have to find this out. So let's do the LHS first. Expected value of xz, this is equal to expected value of x into x square, that is expected value of x cube. What will be the expected value of x cube? Integral for this uniform case, this is defined from -1 to 1. So that will be, this is a PDF, a continuous random variable. So -1 to 1 x cube f of x x dx. What is f of x? This is equal to half. We have seen this. This is the PDF here. So this is a constant uniform, half of the probability of having all the values in this range is half. So this is equal to half integral -1 into x cube into half dx. So I'll bring this half outside. This is a constant, -1 to 1 x cube dx. So what is the integral of x cube? Increase the power by 1 and divide it by the same number. So that is half into, this will become x power 4 by 4 -1 to 1. So this will be, this will equal to 1 by 8 into x to the power 4, and this will be integrated from -1 to 1. So it will be 1 by 8 into 1 to the power 4 minus 1 to the power 4 minus 1 to the power 4 minus 1 to the power 4 will become 1 again. So this will become equal to 0. And what is expected value of x? This is 0. So what will be the expected value of x square? This will be again 0. Okay, x into x. So this is equal to your x square. We know that this expected value of z is equal to 0. This is because this is the expected value of x square. Okay, so this implies expected value of x into expected value of z is equal to 0 into 0, that is equal to 0. So now you see here that this is 0 here and even this is 0. Both are same. But we have seen here that z is equal to x square. Z is directly related to x. If x changes, z changes directly in the square proportion. So we know that z is dependent on x. Although this formula is holding here, although e to the expectation of xz is equal to expectation of x into expectation of z, this holds. but even then, but x and z are not independent, because clearly z is dependent of x. I hope independence is clear now. We have seen enough formulae. So now let's move to the next topic. I want to discuss independence before I.I.D. So what is I.I.D? Now let's understand I.I.D. I.I.D. So this is an abbreviation. This means independent and identically distributed. Independent, we know each sample is independent. Okay, so the value of one sample does not impact the value of other. So with this we know each sample is independent. And identically distributed means that all the samples are coming from the same distribution. Each sample comes from same distribution. Say for example, either it's like Gaussian or normal, whatever, or Bernoulli, Poisson, geometric, whatever, name it. There are like thousands of distributions, at least hundreds. Okay, so this is generally used when do we use? You must be listening to this I.I.D. wherever in machine learning you will see that the data set, the data is I.I.D. So you will listen to this in I.I.D. assumption, that the assumption is the data is I.I.D. So in that context, you will listen I.I.D, and that means that each sample is independent. For example, if I have a data set that has the height of people, okay, height of people in a city or something, okay, so the sample of heights, so each height here, so what does independence means? The independence term means that each height in that sample is independent of the other height. The height of one person does not impact the height of other person. So that is independent. Identically distributed means all these heights are coming from the same distribution, that is a normal distribution or a Gaussian distribution. So that's what I.I.D means. I hope I.I.D is clear. Now let's move to next topic. This is important. Okay, so the next topic is convergence in probability. Let's understand that. So let me write it down. I'll give you an example, then we'll discuss. The name seems convergence in probability. So this seems a bit theoretical, but this is the basis of a very useful and commonly used assumption that we make. Okay, and the assumption is that, for example, if you have a data again for predicting the height of people, you have a sample, you have a sample of data where you have multiple batches. Okay, each batch is one sample. So and each batch is say of size 100. So you have multiple such batches, and you take the average height of each sample, and this, when you check it out, this height should finally, the average of all this should finally converge to the true average height of the complete population of that city or country, whatever you are measuring. So that's what convergence in probability means, and this is the basis for weak law of large numbers also. So let me write down more theory around this, okay, and give you more explicit examples so that you understand. So what was the use case? That we try to predict the height of people, in a city. That's what was the example in a city. Same example. Let's continue with that. So we are given data in batches. So we have batches of data of size, each batch is equal to 100. Okay, and say there are like n is equal to number of batches, and or say samples, here, and within each sample there are like say 100 data points. Okay, so number of batches or samples is 100. So convergence in probability means that, what does convergence in probability mean? That the number of, as the number of sample n increases, as it tends to infinity, as it becomes more and more, the sample average, okay, the sample average will become very close and close to the true average. Or in other words, the difference between the sample average and the true average will become very small. Okay, let me write it down in words. So what does convergence in probability means? You know this intuitively, you must be using it, but there's a theory behind this. Convergence in probability means that as n, that is equal to, I'll write hash symbol, number of samples, okay, increase the probability of sample average, of the sample average that we have for each sample average, okay, become very close to, or become equal to, become very close to, or become equal to true average. Or in other words, or the difference between sample average and true average becomes very small, very small. Okay, so as becomes increases means, as in mathematical terms we write as n tends to infinity, means we have very large samples. And how is it mathematically written for us? Okay, more mathematically rigorous way, if you want to write, okay, the same thing in a more generic way. Okay, say now we have, so we have understood, this is the intuition, that you have a lot of samples, and as the number of samples increase, as it tends to infinity, because very large, instead of 10, 100,000, as the number increases, the average of that sample will become very close to the true average. It will become true average with very high probability. Okay, as n increases, the probability increases, and it converges to the true average. That's what convergence in probability means. There are two terms: convergence in probability. It converges, the sample average converges to true average, or the desired whatever we want, this converges to the true average or true mean with very high probability. As the sample increases, the probability also increases. Okay, and if you want to write that mathematically and in more generic way, so I'll write it down and then I'll explain it. So the mathematical is that we can, instead of having these, we can have a sequence of any random variable. Say for example, if we have, let me move to the next page. So okay, we have a sequence of random variable, say x1, x2, and so on till xn. So we have a sequence of random variable, okay, and this sequence of random variable is said to converge in probability to a random variable x, okay, that is generally known or a constant or something. Okay, mostly for practical use cases, we know this is the, that is what we expect it to be. Okay, to a known random variable, okay, x, known random variable, okay, random variable x, if for every number epsilon, this is symbol epsilon, this is notation they use mathematically, epsilon. Okay, I'll write it down. Let me use another color. So this is e, this epsilon, this is equal to epsilon, this is the name, that is positive, greater than 0. Okay, the following holds true, the following is true. So mathematically we say that this sequence of random variable converts to this another random variable which is generally known for practical purposes. Okay, if the following holds true, what is the formula? The mathematical formula, that as a limit, we know this limit n tends to infinity, the number of samples increase, the number of random variables that we have here, this n becomes very large and large. Okay, and the difference between, okay, is greater than or equal to epsilon. Okay, the limit. Okay, there's one more thing. So that is the probability. This is what the probability that the difference between the sequence of random variable, any random variable in this sequence, and the target, this is generally called target random variable, is greater than or equal to epsilon, which is our tolerance table, that is a very, very small number, becomes 0. The probability, this probability of the difference being greater than a very small tolerance level, or a margin of error, the difference between these two sequence, the sequence of random variables and the target random variable, the difference between them, okay, greater than being that margin of error that we can tolerate, this probability becomes equal to 0. As n tends to infinity, this probability will become 0. Okay, let me write these terms for you. So this is our, generally this is called our estimator, that we try to estimate something, this x of n. So we have a sequence of random variables trying to estimate something, as we were trying to estimate the average, okay, of height of a city, right? So this is our estimator trying to estimate, and this term is called the, this is generally known, this is the target. Okay, this is generally called the target or limiting. This is a limiting random variable. Okay, mostly the distribution of this is known for practical purposes, or this is a constant value, as we saw in the earlier case, that the mean, that is constant. Okay, so this is what is your convergence in probability. I'll reiterate, as the number of samples, as the number of random variables in this sequence, this n in this sequence, as it tends to infinity, the difference between any random variable in the sequence and the target random variable, that difference is greater than a margin of error. This epsilon is margin of error. Okay, this epsilon, okay, is equal to, this is called tolerance level, that how much difference you can tolerate, tolerance level or margin of error, or basically how close you want these to be, these sequence of random variables and the known target random variable, the difference between them being greater than the smallest value that we want, that is our tolerance, that how much we can tolerate, 10%, 1%, 0.01%, the difference between them, as n increases, this will, okay, this probability will become 0, and that's what is your convergence. This xn will converge to x, that's what the convergence term, and the probability, this will increase as n tends to infinity. That's why you say that this is not all sure, but as n increases, this will become, the probability of this becoming equal to 0 will increase. That's why we say convergence in probability. I hope that is clear. And let me write one more term here that is missing for mathematical recall, that this is for all epsilon greater than 0. This is for all, mathematically for all. This is epsilon greater than 0. So this is some positive value depending upon how much difference you can tolerate between the sequence of random variables and the target random variable, or the limiting, that's the limit that you want it to hit, that this sequence should converge to this random variable. I hope convergence in probability is clear. Let's move. I'll give you an example that will make you this example very clear. For example, let's define the sequence of random variables and the target random variable, or the limiting random variable, with the coin toss example. For example, I toss a fair coin. toss a fair coin, and I'll define my sequence of random variables, that is x of n is equal to, so this will be equal to n by n plus 1 if head, and this will be equal to 1 by n if tail. This is how xn is defined, and my target or limiting random variable is, this is our Bernoulli, simple 1 if head and 0 if tail. So I want this sequence of random variables to converge to unknown Bernoulli trials. This is our Bernoulli, right? This is our Bernoulli. So what will be, let's understand this mathematically now. So this problem statement is that whether this will converge to this or not, and we have to see whether what is the convergence probability. So xn will be, xn means x1 x2 x1 x2 till xn, and this n is the defining n here. So let's see. So if xn is defined as x is defined like this, what will be xn minus x? We want to find out mod of xn minus x. So xn minus x will be equal to n by n plus 1 minus 1 if head. So okay, let me write it again. N by n plus 1 minus 1, this is equal to n minus n minus 1 by n plus 1. This n goes, this is equal to minus 1 by n plus 1 if head, and this will be 1 by n minus 0, this is equal to 1 by n if tail. This is my xn minus x. What will be my mod? Because I'm tolerating, the tolerance level is on both the directions plus minus, so I take a mod on that. So this minus 1 by n will become 1 by n plus 1. This negative sign goes because of modular. Okay, if head, and 1 by n if tail. So this is how my xn minus x is defined. So I'm just defining my random variables. This is there. Now let's check. Say for example, first thing, say n is equal to 5. So what will be my mod of x? N is equal to 5. What will be my mod of xn minus x? This will be equal to 1 by n plus 1 and 1 by n if head, and this is if tail. So this will be equal to, n is 5, this will be equal to 1 by 6 and 1 by 5 if head, if tail. So this will be equal to 1 by 6 will be like 0.16, and this will be 0.2 if head, if tail. And let's define our epsilon also. Say for example, my epsilon is equal to 0.1. I want 0.1 tolerance, 10%. 0.1, very small number. So now if we see that both these numbers of getting a head and a tail, both of them is greater than 0.1. So for n is equal to 5, this is my tolerance level. Let me write it again. For n equal to 5, what is this? So what we can say? So for n is equal to 5, mod of xn minus x is greater than 0.1. Okay, this implies probability of xn minus x greater than or equal to 0.1 for n is equal to 5 is equal to 1. Yes, both the cases are greater than 1. So this is equal to 1. So this condition is not satisfied yet. Okay, now let's increase it. This is equal to 1. Now what if n is equal to 20? So my xn minus x is defined as 1 by n plus 1 and 1 by n. This is for heads, this is for tails. This is equal to 1 by 21, 20 plus 1. That is 1 by 21, and this is 1 by 20. So this is equal to, this will be very close to, this is very close to 0.05, and this will be also very close to 0.05 only. This is if head, if tail, right? So now if you see, and my epsilon is 0.1, and it's 0.1. So can we say that for mod of xn minus x, okay, for n is equal to 20, now I'm increasing my n, I'm moving towards infinity, mod of xn minus x is less than 0.1, this 0.05, and this will be definitely less than that, this will be approximately equal to, so this is less than 0.1. This implies my probability of mod of xn minus x less than 0.1 will become 0 now. Yes, this is 0.05, so this value will never cross 0.1, my tolerance level. So the being less than, okay, or equal to, sorry, this is less than, sorry, not less than, greater than, ulta. This is my formula, right? So I'm just, let's check the formula. Greater than, yeah, greater than. Oh, so that's what I meant. So this being greater than or equal to 0.1 becomes 0. Yes, because 0.05 is less than 0.1. So now this probability holds for n equal to 20. We can understand that, say 1 by 10 is equal to 0.1. This implies for n is equal to 10, this will hold. Okay, for any value greater than or equal to 10, this implies that for all n greater than equal to 10, probability of mod of xn minus x greater than equal to 0.1, that is my epsilon, will be equal to 0. This is for all, and my epsilon is equal to 0.1. That's what that is my tolerance level. So for any value greater than, any n greater than 10, my probability equal to 0 will hold. Similarly, okay, so if I write it, so if I extend this, okay, so similarly we can say that now let's increase the tolerance level. For example, if now n is equal to 0.01, if n is equal to 0.01, if epsilon is equal to 0.01, then what will be my n? So for all n greater than equal to 100, probability of mod of xn minus x greater than equal to 0.01 will be 0. And you can just keep on doing this. You can increase n. As you increase epsilon, your tolerance level, your n will increase, right? So similarly, this can be proven for this also. Similarly, you can keep on going. So this epsilon can become very, very small. So even if become like 10 to the power minus 10, similarly, you will have to take those many samples and will become that number corresponding to this. This will become, n will be greater than equal to 1 by 10 to the power minus 10, that is equal to 10 to the power 10. If I have these many samples, so I can get this within this tolerance level, within this range, okay, with very high probability. When I have these many samples, I can say that xn minus x, this is sequence of random variables, will converge to x with this any epsilon that is greater than 0, the tolerance level within which I want. So this should be greater than 0, but this can be very, very small. The tighter you want these to be, the number of samples will increase. So depending upon the tolerance level that you have, the n will change, and as corresponding this, as whatever is the number that will change 10 to infinity, you will get that tighter bound, that this are very, very close, and that bound is defined by this tolerance level epsilon. Okay, so that is your convergence probability. As n increases, the probability increases. So you can say that this is enough to conclude now. So we can say from this example, therefore this is enough to conclude that limit n tends to infinity, probability of mod of xn minus x greater than or equal to epsilon will be 0 as n tends to infinity. That is, how do we write it symbolically? You will see so many places that xn will tend to x with some probability. So this is convergence in, this is what is your convergence in probability. And with this follows your next thing is weak law of large numbers. Okay, so what is the probability here? That the likelihood that xn is close to x. So what does this probability means? That likelihood that xn is very close to x depending upon the tolerance level you have set. Okay, so this is what probability means. So the next topic is weak law of large numbers. This is the theory for weak law of large numbers, and we'll continue the same example. And this is used everywhere in statistics and probability, and wherever we see, right, this is used widely when we solve anything. We'll see it again in statistics, and we'll because of this law, we'll assume that the sample average can be assumed to be a good estimation of the population mean. Okay, this is what it says, that's sample mean will be close to population mean. So in statistics we assume this because we cannot have the complete samples data. For example, even in a city you cannot get the height of each and every person height. So you take out samples from that and you calculate the average, and then you say that this is the average, and that is bound to be very close to the height of an average person in the city. This is because of this law only, weak law of large numbers, and the theory behind this is because of convergence in probability. Okay, this is how all the things add up together. So what is, okay, so there's one more thing that it does not, okay, what does it guarantee? It does not guarantee that average. It doesn't give a guarantee, okay, but it says that it does not guarantee that average will be close. The word guarantee is not there, that average will be close. It will be close, but it does not guarantee that it will be close, but says that the probability of being away from the mean is very low. Okay, but says that the probability of the average, sample average, right, sample of it being far away from true mean is very low. So it does not guarantee that absolutely yes, if you have it, okay, as n tends to infinity, this will become, but it says that the probability of it being far away from that actual or true mean is very low as n tends to infinity, as we have more and more samples. So how do we write it mathematically? For example, we have a sequence as we saw for convergence in probability, right? For sequence of random variables and their IID, we have studied IID also just now. IID means independent and identically distributed. Random is IID random variables, that are IID, x1, x2, so on till xn. We have n samples with true mean, okay, with the true mean is equal to mu. The sample mean converges to mu. How do we write it mathematically? Mathematically we write that xn, this is bar. This bar here means sample mean of the sample average. This is a sample mean or sample average of the nth sample. This will tend to mu. So this is, and let me make it bigger, this will tend to mu with some probability as n tends to infinity. This is a shortcut of, this we write the same thing in short form. This is a short form of this thing. So in short we write like this. Okay, same thing we're writing in short. So this is the short for this thing, that sample mean and this is the true mean or population mean. Okay, so this will tend to mu in probability. This will converge to the mu or the actual true mean in probability, and the probability will depend upon how close you want to be. Okay, it will depend upon the epsilon or the tolerance level that you have. So as and the number of samples you have, as n tends to infinity and the epsilon, this will converge in probability towards this sample mean, and this comes from convergence in probability that we have seen here. This is coming from this theory. Okay, this whole thing, let me highlight this also. I hope convergence in probability and its application, the immediate application in weak law of large numbers, is clear, and the application of weak law of large numbers in statistics is also clear, that sample mean will be close to the population mean, and if you have a sequence of IIDs, then the sample mean converges to, we use this as a rule readily, but this is because of this weak law of large numbers. If this is clear, let's move to the next point. So this is related to, so this was weak law of large numbers was an application of convergence in probability. Let's see another kind of convergence, that is called, so you know the theory in convergence in probability, we have discussed it at length. Now I'll use that understanding to make you to discuss the next convergence, that is almost sure convergence. That is almost sure, I told, right, with probability is equal to 1. So I'll write the formula for it directly. All the things remain the same, all the intuitions remain the same. So probability equal to 1 means almost sure. And why probability is equal to 1 is not certain but almost sure. I have discussed this in another video also. I'll put the link. Okay, so what is here? So what does it mean? We say that sequence of random variable xn, okay, where n is greater than or equal to 1, converge to x, that is the target or limiting target or random variable, if now you see the thing, earlier the limit was outside, now the limit is inside. The probability of limit n tends to infinity xn equal to x becomes 1. How do we read this? And this and how do we write this? This way we write it as xn tends to x almost sure, or we write xn converges to x with p is equal to 1. Okay, so here you see earlier in convergence in probability, what was there? The probability of this difference of sequence of random variables from the target is greater than or equal to some tolerance level. This becomes 0 as n tends to infinity. Okay, and epsilon was a very small number, greater than 0, that was our tolerance level. But what is happening here, that the probability of xn becoming equal to x as n tends to infinity becomes 1, that it becomes almost sure that as n increases, as we have more and more samples, this n will tend to x, this will converge to x. We are almost sure about that with probability equal to 1. So this is what almost sure convergence means. I hope the theory is clear, and let me give you a small example, and then I'll go to the next application of this, that is strong law of large numbers. So this is a theory for that, and proving this is a very strong, okay, this is very okay, this is hardest to satisfy amongst all convergence. There are other types of convergence also, for example convergence in distribution, convergence in rth mean, etc. So there are other convergences, but we'll discuss about convergence in probability and almost sure convergence. And out of all the convergences, that some sequence of random variable will converge to some other kind of random variable which is known, okay, or which we want, that is the target. So this convergence is hardest to prove among all the convergences. It has got a very long mathematical proof which is beyond the scope of this. But the earlier one, the convergence in probability, that can be proven, that can be easily proven using the Chebyshev inequality, which I'll discuss in the next video. I'll put the link also. Okay, so that is easy to prove, but this one is hardest. Okay, this is hardest to satisfy, and the proof is also very difficult because this is hardest to satisfy because this is a very strong statement, hardest to satisfy. Okay, amongst all convergence. So that a sequence of random variable will converge to some other random variable. Okay. And now if we can say that this is the strongest of all this. So we say that if xn, okay, if it's xn converges to x with p is equal to 1 or almost sure, this implies that this we can say that xn will converge to x with convergence, it will converge to probability. If it is converging in almost sure with almost sure probability, it is converging to x, then we can say that it will converge in probability to x. But the other way around is not true. This is a stronger statement and harder to satisfy. But the other way around is not true. We cannot say that okay, and cannot say the other way around. So if it is like this is not, yeah, let me write it this way. This is not the case. If something is converging in probability, we cannot say that this will converge with probability equal to 1 or almost sure. So here this is almost sure. The other way around is not true. If this is satisfied, then this we can say, but if this is satisfied, then we cannot say this. I hope this is clear. Let me give you a small example here. Okay, this is a very toy example, but this will make things clear. Okay, for example, you have x is a random variable such that x1 equal to x2 is equal to so on till xn is equal to half. This is a constant, and then y1, y2, yn is another random variable such that y1 is equal to x1, y2 is equal to x1 plus x2 by 2, y3 is equal to x1 plus x2 plus x3 by 3, and so on. Okay, if this is there, then we can say that this implies yn, that is equal to average of these random variables, I equal to 1 to n xi. This will converge to x, that is half, and this will be almost sure or with p is equal to 1. I hope this example makes it a bit clear that these are the two random variables. So practically we don't use this so much, but this is good to know. But this is the backbone, okay, for strong law of large numbers, and we use that for in all the machine learning to make the assumption clear that why are we assuming that the output of this whatever we are training the data, right? So that will become, I'll give the exact statement later. But if this is clear, this strong, okay, this almost sure convergence is clear. Now let's use this to prove this is the application. The application of this is strong law of large numbers. So that is the next topic. So let me write strong law, and this application will make it more clear. What does almost sure convergence means? What does this mean? Okay, so the strong law of large numbers says that the sample mean will almost surely converge to the true mean or population mean. Okay, so the sample mean will almost surely converge to the true mean. True, or we say sometimes population mean. Okay, this is what strong law of large numbers says. So how do we write it mathematically? Probability of limit n tends to infinity, x bar, bar is the for the sample of nth, will become mu with one probability. This is your sample mean and this is your true mean, and this is coming from your almost sure convergence. And how do we write it in terms of the symbol? So symbolically for it, 1 by n sigma I equal to 1 to n x of I, this is your sample mean, will converge to your expectation of x, and this will be almost sure with p is equal to 1. But there are some assumptions or requirements to fulfill, that the mean and the variance should be finite. Mean and variance of each sample should be finite. That's the requirement. Okay, so this and this is for xn. So IID random variables x1 x2 till xn. So this is for this I equal to 1 to 1. So all these random variables, this should be independent and identically distributed. They should be independent of each other, the height should be independent, and then they should be identically distributed, means that they should come from the same distribution. So these are my IID random variables x1 to xn. So this is much stronger statement, and then this is a statement about the entire sequence. Okay, entire sequence. Okay, this is about the entire sequence of numbers. For example, let me give an example that will make you the difference between. So generally, what's the difference between strong law and weak law, right? For example, if you toss a coin, okay, so if you toss a coin with a fair coin that has 0.5 probability of heads and tails, so if you toss the coin multiple times, say infinite number of times or very large number of times, then the number of heads, okay, the count of heads, that will converge to 0.5. That will be the half of the tosses will get head, and that will converge. Okay, so that will converge with probability equal to 1. This is what strong law of large number says. Okay, if as n tends to infinity and the chances of getting any odd sequence is 0, the probability of getting any sequence that is an exception to this norm, that will become 0. That's what strong law of large number says, that as n tends to infinity. But for weak law of large number, what does it say? That weak law of large number says that if you toss a coin in large number of times, okay, and the proportion of heads will probably be very close to 0.5. Okay, that will be very close to 0.5, and but it does not rule out. So with some probability, as it converges in probability, right? So but it does not rule out the probability of seeing an odd sequence. Like if you do 10 sequence after you have done, say for example 1000 heads, and that will be the proportion of head will be close to 500 or 499 or something, or 501, that will be very close. But after you have seen 1000 tosses, it does not deny the possibility that the next 10 tosses, all of them will be head. That means that it's not guaranteed that you will get only 5 heads. It's possible that all the next 10 heads can be next 10 tosses can be heads. This weak law of large numbers. But in strong law of large numbers, this possibility, the probability of seeing such a an odd sequence of events, right? This becomes zero. This, I hope, with this the difference between weak law of large numbers and strong law of large numbers, that is clear. And one more application of strong law of large numbers is that it ensures the when you train the models, right? AI models are trained. So when we train the model, so it guarantees models reliability by guaranteeing that the average error that we see on a very large data set, the the terabytes or terabytes of data on which GPT etc. is trained. So when we see a very large data set, here n tends to infinity, so the average error on large data set will converge to the true error. That's what it ensures. It ensures model reliability, and thus when providing the confidence that when these models are tested on unseen data, they will give me accurate results. This is an application of the strong law of large numbers. Okay, lot of theory to understand, but this is the application. Okay, let's do a quick revision at the end so that everything is clear. Things are simple, but putting it in words is difficult so that it gets into your head. So summary or quick revision of what we have studied today. So we started with independence of random variables. So independence of random variables is that outcome of one random variable does not impact the outcome of another random variable. And we saw the bunch of formula which essentially means that if it is a CDF, we saw CDF, PMF, PDF and expectation. We saw that the joint probability of two random variables should be equal to product of the individual random variables probability. So similarly, is the case with fx. This is the CDF, the PMF, and then the PDF also. The thing is that it is the product. It is the product. It is the product. And the similar thing is for the expectation. Expectation of xy is equal to expectation of x into expectation of y. Then we saw that for independent random variables, variance of x plus y is equal to variance of x plus variance of y, because covariance of independent random variables is 0, and that is because of the expectation criteria fulfilled. After this, we saw some examples to understand that, and we also saw that that if expectation of xy is equal to expectation of x into expectation of y, this condition is fulfilled, then we cannot say the other way around, that x and y are independent. If x and y are independent, then the product, the combined probability or expectation should be the product of individual expectations. But if this is satisfied, it doesn't guarantee that the two random variables x and y will be independent, and that we saw through the examples also. Okay. Then next we saw convergence in probability, means for sequence of random variable, which is when we try to do an estimate of average height of people, then the sequence of random variables will converge to a known random variable or a target random variable. Okay, and the probability of it, okay, that the difference between the sequence and the target random variable is greater than some tolerance level, this becomes 0 as n tends to infinity. We understood this with example also. And then we move to the application of this. We saw this, we proved it theoretically. Then we saw the application of convergence in probability to weak law of large numbers, which says that sample mean will be close to the population mean. Means the difference between the sample mean and the true mean, okay, that will be very, very low as n tends to infinity. The difference being, the probability of that difference being some non-zero number will be, or being far away from the mean, will become very, very low as n tends to infinity. And this is how we denote it, that xn converges to mu. This is sample mean will converge in probability to mu. Okay, and the next thing we saw was almost sure convergence, means almost sure means probability is equal to 1, and that it is a more stronger guarantee than convergence in probability, that a sequence of random variables xn, x1, x2, xn, okay, that will converge to a target x random variable x, okay, and the probability of that will be 1. as n tends to infinity, and it is denoted by xn as almost sure or with probability 1. Okay, this is hardest to satisfy among other convergences. There are other convergences, types of convergence also. And the one more thing was that if xn converges to x with probability 1, then we can say for sure that xn also converges to x with probability, converges in probability to x. But if xn converges in probability to x, we cannot say that it converges to x with probability is equal to 1. The other way around, 1 is not true. This is not true. Okay, this is the most stronger. Then we saw a toy example to understand this, and then we saw the application, that was strong law of large numbers, where sample mean will almost surely converge to the true mean as n tends to infinity. So this is the formula that as limit tends to infinity, the sample mean will converge to mu with probability is equal to 1, that is almost sure. Okay, and then we saw the example of coin toss that I discussed, that if you, the difference between weak law of large numbers and small law of large numbers is that if we toss a coin, say 100 times, 1000 times, so weak law of large number says that the probability of seeing a sequence which is odd is not denied. We can see. So for example, I have tossed a coin 1000 times, and there are, like, say around 500 should be heads, right? The count of heads should be 500. But if it is 490 or 499, something like that, but even then it will be around 500. But even after 1000 tosses, we cannot guarantee that the next 10 tosses will not be a head. That's why it's called a random variable. Okay, and that is converging in probability. So even that sequence is possible. But the strong law of large number says that this is not possible. The probability of such an event happening is 0. So that's the simplified difference between weak law of large numbers and small law of large numbers. Okay, so that's all for this video. Thanks for watching. Have a good day. Bye for now.